Hello guys, this is 10.3, the integral test. So here we're introducing another test to test for convergent and divergent. Now before you can decide on whether to use this test or not, the function that we're looking at must satisfy these three conditions. First is continuous, positive, and decreasing. Okay, on the interval k to positive infinity, where k is some constant, positive constant. Right, then we can say that the series, which is the sum of all the sequence, and then the function is basically the sequence, is convergent when the integral going from k to infinity is convergent, and it's divergent if the integral is divergent. Note that the function does not necessarily have to be decreasing for all x uh, within the domain. It's just that as long as the function is decreasing eventually, right? So let's say I have a function k right here, and then let's say the function is like this, right? And then as long as it's decreasing at the end, this is fine, right? What we don't want is something like this, where you get something like that, right? We don't know if it's going to decrease or increase, but as long as the function is decreasing eventually, then we should be fine. All right. Now there is some number capital N, so that uh, f is decreasing for all x greater than capital N. Right. So the capital N in our case would be somewhere around here. Right. Capital N. When x is greater than capital N, it starts to decrease. Right. But here we cannot find like a certain point of capital N where the function is decreasing, right? So in this case, we can use integral test for the first example, but not the second one. Okay. All right. So next we have a few slides, a few example that will show us, give us a good idea of how the integral test is working. All right, so here we have our first function, which is 1 over x. So keep in mind that this represents a sequence, right? So if we write out the sequence, that will be 1 over 1, 1 over 2, 1 over 3, and 1 over 4, and so on, right, to infinity. Now, from 1 to infinity, we know it's continuous, it's positive, and it's decreasing, right? Everything we get from 1 over x, when x is positive, the whole thing is going to be positive. And since we're not including 0 in our domain, it's always continuous to the right hand side of 1. And it's decreasing, right? Because when we increase the value in the denominator, the function is decreasing. All right, so once we have checked these three property, then we can go ahead and perform the integral test. Okay, so here's something to show you some great idea that when we add up the little rectangles here, it's an overestimate of the integral for 1 over x, right? This is an overestimate, but we are not going to worry about this case. Uh, this is the right sum, Riemann sum. All right, so let's check out the integral test. All right, so we're going to take the integral from 1 to infinity, given from the question of 1 over x dx. So the integral test says if this thing converges, then the series will converge. If this integral diverges, then the series will diverge. All right, so let's see what we have. That's an improper integral, so introduce the limit. Okay, 1 over x dx. And then go ahead and integrate it. We have ln of x going from 1 to t, which gives us the limit as t approaches infinity, ln of t minus ln of 1, which is 0. Right? And when you take the limit, you get infinity. Means diverges. Okay. And since we know that this thing is smaller than the sum that we're looking at, we can say that the series sum, infinite sum of 1 over n diverges. And this special series has a name, right? If you're adding a 1 over n, this is called the harmonic series, which we'll look into more details in the next section. Okay. Next, we have 1 over x to the power of p. Right, so this type of function, it works like a power function, but it's in the denominator, right? And then we're looking at it from 1 to positive infinity. And the question is, for what p-values does the integral converge, right? We want to figure out what is the condition on the constant p so that this function will converge, or this series. Okay, so um, let's say, before we get into the details, let's just say if p is equal to 2, right? Then we have 1 over n squared, right? Which will look like 1 over 4, 1 over 9, 1 over 16, right? Dot, dot, dot. All right, where n is equal to 1, 2, 3, 4, and so on. Right, and then you get the idea. If p is, let's say, 1/2, right, then it's 1 over n to the power of 1/2, which would be 1 over rad 2, 1 over rad 3, and so on. Okay, so we want to figure out what type of p-values, what's the condition of p-values so that this series will converge. All right, so let's go ahead and perform the integral test. Now, again, before you perform the integral test, you want to check 3 things. A, continuous. B, is it positive? And C, is it decreasing? Okay, now we're looking at for x greater than or equal to 1, right? So it's going to be continuous because we don't have 0. So yes, continuous. Is it positive? Well, this whole thing is positive, and the x value we're looking at is also positive. So yes. Now decreasing can be a little tricky to check, but one way is to show decreasing is to show that f prime is always negative, right? F prime represents increase or decrease of the function. Right, so let's do that very quickly. So f of x is x to the power of negative p. Then f prime will be negative p times x to the power of negative p minus 1. Right, so this negative p here is always going to be negative, and then our x is always positive. Right, so the whole thing is going to be negative. So the whole thing will be negative, which means decreasing. Okay, so that we have checked these 3 conditions, we are ready to proceed with integral test. Let's go ahead and do that. Integral from 1 to infinity, 1 over x to the power of p dx. All right, and again, that's an improper integral, so introduce a new variable, t, taking the limit to infinity, going from 1 to t, x to the power of negative p. All right, and then dx. We have limit as t goes to infinity, x to the power of negative p plus 1 over negative p plus 1, going from 1 to t. All right, so let's see what we have. Limit as t to infinity, that will be t to the power of negative p plus 1 over negative p plus 1, and then minus 1 to this many powers, so it's 1. All right, so let's see what we have. First, we need this thing to be less than 0. Right, now the reason that it has to be less than 0 or negative is so that we can or this thing right here, so we can move this whole thing to the denominator, right? We want negative p plus 1 to be less than 0, so we can move the x term to the denominator. right? Our goal is to keep the x in the denominator so that it will converge, right? So the goal is we want negative p plus 1 to be less than 0, which tells us that p has to be greater than 1, strictly greater than 1. All right, so then if it's greater than 1, then it will diverge. It will converge, sorry. If p is greater than 1, then the integral will converge. So what can we say from this result? There are two cases. First, the infinite series of 1 over n to the power of p converges when p is greater than 1, strictly greater than 1. In part 2, the infinite sum of 1 over n to the power of p diverges when p is less than or equal to 1. Okay, and this is the result that we can use, right? When you have these type of series, you can just recall back to the result that we have from this example, right? 1 over n to the p, this infinite series will converge when p is strictly greater than 1, 1.1, 1.2, and so on, right? 2, 3, 4, and so on. Now, if p is less than or equal to 1, then it will diverge. If you take 1, for example, if p is equal to 1, you have 1 over n, which is what we had earlier in this example, right? 1 over n, and we have shown that it actually diverges right here. And when p is equal to 1, that's the harmonic series, okay? And we actually have a special name for these cases when you have 1 over n to the p. This is one of the famous one of the ones we're going to see a lot. This is called the p series. Okay, so for p series, it will converge when p is greater than 1. Okay, just keep that in mind. All right, let's do another exercise. Here I have 4 infinite series. Now they are all p series. Go ahead and take a minute, pause the video, and determine whether they converge or diverge given our result from above, the p series result, okay? All right, so the first one, p is equal to 5 over 2, which is about 2.5. That is greater than 1, right? So it will converge. So we can say that p series converge with p equal to 2.5. Okay, let's look at part B. Now b, in this case, 1 over radical n is 1 over n to the power of 1/2. In this case, p is 1/2, right? So we say p series will diverge with p equal to 1/2 or 0.5, right? Which is less than or equal to 1. Part C, now this is a little different, right? We have the 3 and the 2. Now notice that they are still constant, so we can actually bring out the constant like this. Bring out the constant of the infinite series. And then now inside we have a p series with p equal to 3, right? So p series converge with p equal to 3, which is greater than 1. All right. And the last one, D, that is 1 over n to the power of e, right? In this case, p is equal to e, right? Therefore, we can say p series converge with p equal to e, which is, again, strictly greater than 1. Right, so you can see that if you have any infinite series in the form of 1 1 over n to the power of p, we can easily determine whether the series is going to converge or diverge by identifying the value of p. Following these two rules, right? Converge when p is greater than 1 and diverge when p is less than or equal to 1. All right, so after P series, let's look at some more general infinite series, and we can better understand the integral test. All right, so let's start with A. All right, we have this infinite series, 1 over n squared plus 4, and we want to check if this converges or not. All right, so first, let's find out the function, right? So the function is basically just 1 over n squared plus 4, right? So we can rewrite that as 1 over x squared plus 4, just replace the n with x. And again, the three conditions you want to check: continuous, positive, and decreasing. Okay. All right, so is it continuous from 1 and up? All right, so x greater than or equal to 1. Oh, yep, check. Positive, check. Decreasing, right? Again, we can check that by taking the derivative. All right, so let's do that. So f prime is going to be, it's going to be negative 1 over x squared plus 4 squared times 2x. Right. Now, since x is always positive and x squared plus 4 quantity squared is always positive, this negative sign will make it always negative, right? So yes, it's decreasing. All right, so let's go ahead and perform the integral test from 1 to infinity. 1 over x squared plus 4 dx. All right, and again, this is need to take the limit to infinity, 1 to t, 1 over x squared plus 4. All right, and 1 over x plus 4, that looks like a arctangent, right? So do a quick review here. Integral of 1 over x squared plus a squared dx is arctangent of x over a. All right, and then what do we have? We have arctangent of x over 2 going from 1 to t. All right, and then that gives us limit as t approaches infinity of arctangent t over 2 minus arctangent 1/2. All right. Oh, 1 over a. Forgot the 1 over a in the front. So it's 1 over a times arctangent x over a. So we have a 1 over 2 out the front. Like that. Okay, and let's see. When b approaches infinity, right? We don't know, right? We don't know about this term, right? But when arctangent is approaching 1/2, well, actually, when arctangent of infinity, this is pi over 2, right? So let's do a little side note here. Right. So arctangent of x approaching pi over 2 as x approaches infinity. Right. So this first term here is gonna be approaching pi over 2. So 1/2 times pi over 2 minus 1/2, and arctangent of 1/2 is actually you can type that into the calculator. Let me do that real fast. It's about 0.46 radian, right? All in all, this is going to be some constant, right? Pi over 4 minus 1/2 times 0.46, right? Which is a nice number, right? A constant, right? So that means it's going to converge, right? So the integral converges. That means the infinite series 1 over n squared plus 4 converges. Okay. All right. So let's part A is going to converge. Let's try part B. All right. So part B, we have the infinite series going from 2 to infinity, 1 over n times ln of n. Let's double check that. Yep. All right. So again, if you guys want to try this out on your own, feel free to pause the video. Else, I'm going to keep going. All right. So f of x is 1 over x ln x. Is it continuous? Greater than 2, so that's fine, right? If it's 1, then it's going to be discontinuous because we get a 0 here, right? But since x is greater than or equal to 2, we're fine. Yes, it's continuous. Is it positive? Yeah, I mean, it's always going to be positive because x is positive, okay? Is it decreasing? Right? Oh, that's where we can check again using our f prime, right? So f of x is 1 over x ln x. Right, so let's do f prime. What is that going to be? Oh, this is a little crazy. Okay, so that's going to be x ln x quantity square. I'm doing a quotient rule, right? Quotient rule. So I have that's 0, so minus ln x plus x over x, so 1. Right. Yep. Okay. Right. So this thing in the parentheses is always going to be positive, so the whole thing will be negative. Right. That means it's decreasing. Okay. So if you are a little confused on how I got this, I just did a quotient rule. Right. In the numerator, just 1, and denominator is g, and then in the parentheses, I have to use the product rule to find the derivative. Okay. All right. So now that we know the integral test is going to work, let's go ahead and check. Taking the integral from 2 to infinity, 1 over x ln x dx. All right, let's see. So again, use the limit. Integral from 2 to t, 1 over x ln x. All right, dx. Okay, so to integrate this is actually quite a little fun. We can use u sub, right? Let u be 1 over ln x. Oh, not 1 over ln x. Let u be ln x. Right, so du will be 1 over x dx. Right, so what we have here will be limit. We have 2 to t, 1 over u du. All right, 1x dx, 1 over x dx. That's the whole thing is du, and 1 over ln x is 1 over u. And that gives us ln of u. And then we're taking x from 2 to t, right? So here to evaluate from 2 to t, we have to convert that back to back from u to t. All right, so I'll get ln of x going from 2 to t. Okay. All right, here we go. So limit t to infinity, ln of t minus ln of 2 Now we know ln of 2 is going to be finite, right? But ln of t, as t goes to infinity, this whole term will approach infinity, right? This whole thing will approach infinity. So it's infinity. Therefore, diverges, right? The integral diverges. Then we can say that the infinite series from 2 to positive infinity of 1 over n ln of n will diverge. Diverges by integral test. Okay. All right. Last but not least, let's check our last one. Part C, that is infinite sum from 2 to infinity of ln n over n squared. All right. So let's see. F of x is equal to ln x over x squared. All right. Again, the three things. Continuous, positive, and decreasing. Right. So is it continuous? We're looking at 2 and up, so that's fine. Positive, yeah, they are both positive. Decreasing, so we know that x squared actually grows much faster than ln x, so it's going to be decreasing. But we can always check using f prime. Right. In fact, I would, when I was doing this, I would always check if it's decreasing by looking for f prime, and it's not too bad. Let's just find it, right? So quotient rule, x squared, and then f prime g, so that would be 1 over x times x squared minus 2x ln x, which will be x minus 2x ln x over x to the fourth power. So it's 2x, right? So this obviously is greater when x is large. This whole thing is going to be negative, right? It will be negative when x is large. Now, if you want to know exactly how large, then you can actually set the numerator to be less than 0 and solve, right? Let's do that, right? So factor on x, divide, so I get 1 minus 2 ln x. It's in 0, 1 minus 1 is less than 2 ln x. So 1/2 less than ln x. Then e to the power of 1/2 less than x, right? So when x is greater than e to the power of 1/2, this thing will start to decrease, right? And just like what we were saying earlier, it doesn't have to decrease, be decreasing in the entire interval as long as it's decreasing eventually, right? Remember, there's a capital N. So this will be our capital N. This is where the point that the function is going to start decreasing always. Okay. All right. But anyway, that's just some preliminary checking. And now that we know it satisfies these three conditions, we can go ahead and continue with our integral test. All right, ln x over x squared. And again, we have to introduce the limit because it's an improper integral. Okay, so now here we have to do some sort of integration by part, right? Because we have ln, we have x squared. It's a little hard to use up, right? So let's do integration by part. I'm gonna let u be ln x, dv be 1 over x squared dx, and du will be 1 over x dx, and v will be negative 1 over x dx. All right, so let's see. That's going to be equal to uv, so negative ln x over x. Oops. Oh, there's no, there shouldn't be a dx in the v. Right. There you go. Okay, and then minus v du, so minus v du, so v is negative. I'm going to put that out here, make it a plus. V du 1 x squared. going from 2 to t. Right, and this thing is going from 2 to t as well. We'll take care of that in a second. Right, limit t to infinity. Right, so this whole thing, negative ln x over x. Integral of 1 over x squared, as we saw earlier, is minus 1 over x, going from 2 to t. All right, let's see what we have. We have limit as t approaches infinity, negative ln t over t minus 1 over t, minus parentheses, negative ln 2 over 2 minus 1 over 2. So now this whole thing is a constant, right? So we don't have to worry about that. All we have to worry about is when we take the limit, whether this thing will go to 0 or not, right? So we care more about this part right here. All right, so let's see. So limit of negative ln t minus 1 over t. Now, when you take take the integral, you're gonna get infinity over infinity, or negative infinity over infinity, right? Which is indeterminate form of limit. All right, so we can do a L'Hopital's rule. L'Hopital's rule. All right. So limit as t approaches infinity, that will be negative 1 over t minus 0 over 1, which will give you, so this whole thing is going to go to infinity, 1 over infinity. So that's going to go to 0, which means it's going to converge, right? So the integral is going to converge, this whole thing, right? Let's rewrite it. So integral of ln x over x squared converges. Therefore, the infinite sum that we started with, ln of n over n squared, converges by integral test. Okay, so you can see that we're using integral, mainly integral in this section, right? So the integral test is very nice, right? Pretty easy to work with. It's just have 3 preliminary conditions, right? These 3 conditions that we were talking about, right? Is it continuous, positive, and decreasing, right? Let me go back to earlier, right? These 3 conditions, they have to satisfy, they have to be true for the function in order for you to apply the integral test, right? Once you have checked that the function is continuous, positive, and decreasing in that interval, or eventually decreasing in that interval, then you can apply the integral test, right? Is it convergent? Is it divergent? Right? And this test is pretty strong, pretty good in terms of coming into a conclusion, right? Unlike our previous test for divergence, which only tests for divergence, doesn't test for convergence. But the integral test, they check for both, only with the function that is continuous, positive, and decreasing on that interval. Okay, so that will be all for 10.3, and I will see you next time.